So you can't show documents.
Good evening everybody, welcome to the February meeting at the North Staffs ICTa, the roadshow event. So welcome to everyone here at Potclays, and also welcome to everyone around the country who I hope can hear us loud and clear. Andy's nodding at me, so you must be able to hear me loud and clear. Particularly thanks to Potclays tonight for providing this venue for us, and not only that, but to, I'm sure, the excellent speakers. First we've got Harry Frazer, who's going to talk to us about clays and glazes in firing craft ceramics. Harry's a former MD of Potclays, author of several textbooks, which I see are available on the stand to my right for you to purchase. And Harry was responsible for diversifying Potclays from really just being a clay company to all sorts of things, glazes, kilns, and really moving into the craft sector. Following Harry will be the current MD of Potclays, grandson of the founder of the business. He tells me he joined for 1 year in 1969 and he's still here. So they've not let him escape yet, and prior to that he was a radar design engineer for the Saudi Arabian government. I don't think there's many people who can claim that. So without further ado, I'll hand over to Harry for our first presentation.
Well, good evening everybody, welcome to Potclays. Tonight I want to talk about the clays and glazes that we use in craft ceramics. I should perhaps explain that I joined the ceramic industry back in 1954 and was in the industry for about 10 years or so before switching to the craft ceramic side of the ceramics business. In fact, I remember back in 1954 we were still firing bottle kilns here in Stoke-on-Trent. And people used to say that Stoke was the only place where you could wake up in the morning and hear the birds coughing. But tonight I want to talk about clays and glazes used in craft ceramics. And I suppose we ought to begin by defining what we mean by craft ceramics. Well, we're talking about small-scale producers of...
You have to hold that, I'm sorry.
Okay.
Tell me when to change the slides for you.
Okay, please. So we're talking about small-scale producers of pottery items, tiles, sculptures, models and murals that go on walls. They include the mugs and plates that you see in the craft market, and they include the massive urns around Richard Branson's swimming pool. And very importantly, they include all the pottery items that are produced in ceramics departments in schools and colleges, which provides about 60%, 50% of the business of people like Potclays. But the common denominator is that all these things are made by hand-making methods. Now, clay isn't a very good engineering material. It's got some very awkward properties. It shrinks as it dries, and it shrinks again as it's fired. And if you don't dry it evenly or fire it evenly, it may warp or crack. And the more plastic a clay is, and the softer its consistency, the greater are those problems. And so in industrial pottery production, we generally seek to minimize those problems by using clay bodies of low moisture content and or low plasticity, or use dust pressing, allied to careful drying and firing techniques. And if we need to make some complex shapes, we use slip casting, where we don't need any plasticity, it doesn't enter into the equation. So, clay bodies suitable for industrial use are not best suited for the needs of the craft potter. The craft potter largely relies upon plasticity. Plasticity is very important to craft ceramists. Now, we all know what plasticity is, but nobody has been able to make a machine or an instrument that can properly measure it. We can measure things that are related to plasticity. We can measure the green strength, the tensile strength of clay bars, for example, using a modulus of rupture machine, and compare the strength of one clay with that of another. Because we know that the more plastic the clay is, almost always, the greater the dry strength. And of course, we can also measure the shrinkage. The more plastic a clay is, the more it'll shrink upon drying. So we can measure these things, but it's not really an accurate indication of plasticity, because it only measures some of the factors which make things plastic. Now, a craft potter has got an empirical way of checking plasticity, modelability, workability of clays. He sticks his thumb in it. He throws them on a wheel. He pulls handles with it. And he can tell you about any change in plasticity better than any machine can. So plasticity is very important to craft potters, and Potclays, who specialise in craft ceramic supplies, therefore make a wide range of clay bodies which are made as plastic and resilient as possible for studio use. Resilience is important because with some clay bodies, particularly those made from ball clay, they tend to slump during the throwing operation. So we need a mix which can make the clay more resilient as well as being very throwable. Now, most people coming into craft ceramics assume that the material that they're handling is single clay dug from the ground, processed and bagged. But Mother Nature works with dirty crucibles, and she lays untidy beds. And using a single clay component like that results in a very unreliable and variable product. So we add materials, we blend materials with clay to achieve the properties that we need. If you look at the next one, please. And say we make clays, we've got 65 core bodies in the catalogue, but altogether...
Hold the phone up, Barry. Sorry.
Yeah, we have about 65 core clay bodies in the catalogue, but we produce up to 1,000 other mixes for potters. Potters are able to specify the sort of properties that they need, and Potclays have the technology to put together a clay body to satisfy their needs. So we've got a huge range of clay bodies available. Next slide, please. These are some of the raw materials that we use in the production of clay bodies. Obviously, china clay, kaolin, derived from the granite massif in Cornwall. Ball clays, which we introduced mainly for plasticity, but also give us green strength. Red clays, fire clays. Jonathan Oak will be talking about fire clays in more detail later. And fluxes such as, I mentioned there, Cornish stone. Actually, Cornish stone is no longer available. And in its place, we use Potclays stone, which is a synthetic alternative based on feldspars. Feldspars are widely used as a flux in clay bodies and also in glazes. Next one, please.
Just bear with me, I'm trying to sort out the feedback.
we go. We frequently add flint or ground quartz to introduce the right degree of thermal expansion in the clay bodies firing at lower temperatures. So I'll talk about that in a little while. In powdered form, of course, these things are hazardous, pure silica, and so they carry a hazard label. We use whiting, which is ground limestone. We occasionally need to add a little bentonite, which is an immensely plastic material. We just use it as a plasticizer, particularly in some of the porcelain bodies where we want reasonable throwing performance from a porcelain body. And importantly, we add grogs to many of the clay body formulations. Grogs has become a generic term for a granulate made from a variety of materials. We use corduroite. Fibric grogs were very widely used, but are now not available in this country. Sands are widely used too. Next slide, please. This is the sort of range of clay bodies that are available to potters. We've classified them roughly in terms of the firing range, the lowest fired ones at the top. So we make some raku bodies. Anybody familiar with raku? It's more or less an instant method of producing potteries. It's great fun. You make some clay plates, knobs, what have you, biscuit fire them to about 900 centigrade, stick a glaze on, and put them into an already glowing kiln. So the clay body has to be capable of withstanding the thermal shock and putting them straight in. You leave them in until you see the glaze beginning to soften and smooth over, and then you remove the pot with tongs, and you can bury them in sawdust to get a reduced effect, quench them in water. But it's a form of instant pottery making, and it's quite popular as much as a sort of social thing as any satisfactory means of producing pottery, because raku pottery is very weak. Red earthenware, widely used, firing between 1020 and 1140 centigrade. The low temperature earthenware bodies produced for the hobbycraft market. Hobbycraft's a little different from studio ceramics, but I suppose we should bracket it in the same group. About 10% of all these studio sales is represented by hobbycraft sales, so it's still a relatively small amount. But the hobbycraft body is not very plastic. It's really designed for slip casting. We have white earthenware firing in the range 1100 to 1150. And when we give a firing range, we're really telling you that that's the range of temperature that you have to fire the clay body to achieve its optimum properties. And we'll talk about that a little bit more in the case of the white earthenware, because not firing it high enough is a very common cause of crazing on glazes on the white earthenware. And we have buff earthenwares, and there's a super plastic white earthenware where we use a silicious ball clay allied to china clay and feldspar, and perhaps a very fine grog added into it as well, which is very throwable in contrast with the white earthenware here, which has got a relatively low ball clay content. Next slide, please. Crank bodies are very popular. For people who want to construct slab-built pottery, architectural items, things of fairly thick cross-section, where you want a significant amount of grog so as to reduce the shrinkage, the wet to dry shrinkage, to a low figure. But to retain workability, you need a pretty plastic base to carry that amount of grog. And in crank clays, the grog contents can be up at 40% or more. So that's a lot of grog in the clay body. And crank clays are characterised with a coarse texture and structurally strong and low shrinkage. And we have semi-porcelain and bone china clays. A huge range of stoneware bodies and porcelain bodies, some of which are really quite throwable. We try to make them as plastic as possible, despite the fact that most of the materials are not made plastic at all. But that's why we introduced some ventilate into them. Next slide, please. A typical white earthenware body used in the industry would be made of 25% of ball clay, 25% of china clay, 35% of flint, and 15% of Cornish stone, or Potclays stone, or feldspar. So there's only 25% of ball clay there, and a white earthenware body therefore isn't very plastic. It makes excellent casting slips, but it's not easy to work with. It's not easy to use for hand making ceramic items. Next slide, please. The one on the left is a typical industrial white earthenware body that we've just been talking about. 25 ball clay, 25 china clay, 35 flint, 15% of stone or feldspar, or decolorized. This is a little bit misleading. When I mentioned decolorizing stain, that's a very, very tiny percentage that's added, less than 0.01%. So it's a very minor part of the formulation. But contrast that with the studio white earthenware body on the right-hand side, where we've got ball clay at 70% compared to 25% on the industrial one. Consequently, the studio white earthenware is much more plastic. Industry wouldn't like to use that. The shrinkage would be too high and the risk of warping too great. They would much prefer to use the recipe that's on the left-hand side. Now there are several different manufacturing methods where you come to prepare clay bodies. Can you have the next one, please? Next one. That's it. The standard method for manufacturing clay bodies is to use a slip housing process. This is where we take for example with a white earthenware body, the ball clay, china clay, flint and the stone, and we weigh the amounts that are needed into a blunger and mix all the materials together until it forms a nice slip. And that's then discharged and passed through filters, usually around 120 mesh with the white earthenware body, And then from the filters it's passed over magnets which remove any traces of magnetic iron to help prevent specking. And from there into a stock tank, and we pump from the stock tank into a filter press, and the cakes of clay that come out of the filter press are then passed into a pug mill. The pug mill is just a big extruding machine, and we tend to use de-airing pug mills. Many people use pug mills that are not de-airing, and of course people believe that the small pug mills that craft potters use when they're reclaiming clay, they believe that they take air out of the clay. They don't do any such thing. What they do is they churn up the clay and they break the big bubbles of air into lots of small ones. So all they're doing is just spreading the air. I remember when I was at Podworth years ago, we wanted to make some small quantities of coloured clay, different coloured clays. So a stain was put onto clay slabs, and these were then processed through a small pug mill. And when it came out, it was still badly streaked, so it was recycled, and we kept doing that. And the interesting thing is that after that had been done about a dozen times, we got a bigger volume coming out of the pug mill than we put into it. It was just filling up like air of milk chocolate. So pug mills don't remove air unless they are de-airing pug mills. Next slide, please. Yes, an alternative way, is commonly used in the industry, is to add all the materials by volume individually into a blending tank. I remember when I first started at Alfred Meeking back in 1954, I worked in the Sliphouse for 6 months, and the clay that they produced was produced this way. And the ball clay in one plunger, china clay in another plunger, flint and stone in a separate rotating storage. And they were discharged, and we had a big dipstick. You actually have a dipstick to measure the volume that you're putting in. But it then follows the same procedure. It goes through the filters, through the magnets, to the stock tank, to the filter press, and then into the pug mill. The problem with slip housing comes when you want to add grog. Because for purity, we like to filter the clay body, but if we put grog in at the plunging end, we'd filter it out. And another problem is that if we decided not to filter, and indeed put the grog into the plunger or into the blending arc, the grog settles out of suspension. So, because of those problems, we do have the alternative of adding grog directly into the pug mill. But that's a difficult thing to do. It's very difficult to get an even distribution in the clay if you choose to add grog into the pug mill. So slip housing doesn't lend itself very well at all to incorporating grog into the body recipe. Next one, please. So an alternative is to use a pan mill or a dough mixer and prepare all the powder materials, add the grog with the powder materials directly into a pan mill. Add the required amount of water, and you can mix a very high volume of grog very accurately in that way into a body formulation. The disadvantage with pan milling is that it does rely upon the powdered ingredients that you're putting in not having any oversized contaminant material in them. If a little chunk of brick or something finds its way in, it's going to stay in. The Potclays largely resolved that problem by separately wet processing some of the clay ingredients, so that they put the material in a plastic form rather than in a powdered form after it's been through a full slip housing process. But generally speaking, in summary, generally speaking, slip housing gives you better product uniformity in smooth textured bodies and can also utilize unprocessed raw materials. But dry blending gives a more accurate control of grog and water contents in coarse bodies. It also offers superior plasticity and even blending, even where the body is heavily grogged. Next slide, please. This is just an explanation of the plastic blending that I referred to earlier, where some of the clay materials are separately slip housed and introduced in a plastic form into the panel. So in a way it's a superior process in terms of preventing contamination. Next one, please. Clay plates are, clay particles are microscopically small, elongated plates. And when you pug a clay body, as the clay stream moves through the pug mill, the forming pressure causes the clay plates to line up in line with the axis of the pug mill. In other words, 90 degrees perpendicular to the forming pressure. So what happens is when the clay is extruded, if you look at the bottom left-hand corner, the clay plates have arranged themselves around the edges of the extrusion. And in the inner section of the extrusion, they're relatively disorganized. Now the shrinkage of the center section is going to be a little bit higher than the shrinkage of the outer layers, because the shrinkage in the unit length is lower than the shrinkage when they're in disarray. And that becomes apparent. I mean, I took a few clay slices home with me and stuck them in the freezer. Jill wasn't very pleased. But stuck them in the freezer, and when you take them out and let them thaw, and sure enough, you get the sort of picture that you see in the top right-hand corner, where the clay actually cracks because there's a differential shrinkage. And this phenomenon really is most marked with plastic bodies. With the clays that are not so plastic, if you look at that white earthenware industrial clay, for example, with only 25% of ball clay there, and the other 75% isn't ball clay, that wouldn't exhibit anywhere near the same effect. It's a preponderance of the ball clay that exaggerates this effect. And of course, that could be a problem for studio potters. As we've seen, it doesn't shrink evenly. The shrinkage in the centre section is wider than that on the edges. So potters have to wedge the clay by hand. Now those of you that have seen people throwing pots on a wheel will probably see the potter what we call coning the clay. So once the clay's been centred, he'll lift it up with his hands and then push it down again. And this actually makes the mix much more homogeneous and helps to remove that problem of differential shrinkage. People who are slab building will often take the extrusion and cut it through and smack it down and knead it with their hands, just as people make bread, working dough. So you can break down that effect and make the clay body more homogeneous. And it needs to be done with very plastic models. Next one, please. You get the same effect with bodies which are slip cast. I presume you're all familiar with slip casting. What we do with slip casting is to prepare a liquid slip which is very dense, so that it has a relatively low water content and therefore doesn't have much wet to dry shrinkage. And we prepare the casting slip by using a sodium silicate or soda ash deflocculant. Make a very small addition between 1/4 and 1/2 of 1%, and it has the effect of causing the positive ions from the sodium to move to the negative crystal sites on the clay crystal. Clay crystals have negative and positive sites, a bit like a magnet. And the hydroxyl section, which is negatively charged, moves to occupy the positive sites on the clay crystal. And in theory, that should all balance out. In practice it doesn't, because the large monovalent cations here that move onto the clay crystal don't attach themselves quite so firmly, and they're continually being removed as they attach. So you get an average negative charge on the clay crystal because the positive sites on the clay crystals haven't been fully satisfied by the cation from the sodium. And so you get the clay particles negatively charged, and just like a magnet, if you put two negatives together or two positives together, they repel. And so in casting slips, being negatively charged, they repel each other, and they'll still slip past one another because they're surrounded by a water envelope, but you can get a much denser slip by converting them to a casting slip. With an ordinary clay water slip, you could get a density of about 27 ounces to 1 pint might weigh 27 ounces. With casting slips, you can get 1 pint weighing 36 or more ounces. So you can get a much lower water content and you still have good mobility. The same problem that we had with the pug mill appears, however. You get the clay plates lining up along the surface of the mould, and if the mould joint is not very good, the clay shoots up into the mould joint, and when the cast is removed, you've got a very prominent mould joint section there, which you can fettle away, but because the particles are not all arranged in the same way, when the product is fired, the fired shrinkage of that little section that protruded into the mould joint is a little less than its surroundings. And so although you fettle the thing away, a little blemish still appears on the surface, very marked with bone china bodies. You get this little protrusion from where the mould joint was. The answer is to have very good mould joints, not to use moulds until they're really too warm. Next slide, please. This is put in just to show just a range of white and red earthenware bodies. Next one. Oh yes, we've got a lot of clays. We produce many, many clays. That was an advert that we put out, and it amused quite a lot of people, I think, at the time. I'm not sure whether this slide properly belongs here or in the glazing section, but what we're talking about is the influence of the clay body upon the craze resistance of the glaze which is covering it. When pottery is fired and it shrinks as it's cooling down, if the clay body, or biscuit body, with the glaze on the top of it, if they shrank down the same amount, then you would finish up, in theory, with something like that. With a smooth, unbroken, unmarked glaze sitting on the top of the biscuit surface. If, however, the clay body doesn't shrink sufficiently when the kiln is cooling down during the glaze firing, with the result that the glaze shrinks more than the clay body, then because glazes don't stand tension very well at all, they stand compression fairly well but not tension, the glaze will crack. The glaze will crack. The glaze is now shrinking more than the clay body. Now the shrinkage of the clay body is determined by how high the clay body is fired. In the case of white earthenware bodies that we've been talking about, we typically give a firing range of 1100 to 1160 centigrade. And what we're saying is that you've got to fire into that range in order to get good craze resistance from any covering glaze. And the most common cause of crazing in glazes is that the biscuit ware is not fired sufficiently high to enable it to shrink sufficiently to get a proper match. On the other hand, if the biscuit shrinks too much, then the glaze may not be able to withstand the compression exerted upon it by the squeeze from the biscuit body underneath, and the glaze can fracture and cause a problem we call peeling, where a crack develops and the glaze slips over the crack and you get one edge riding over the top of another. Next one, please. Okay, we're just quickly now going to talk about some firing points. These are some of the typical kilns used by studio potters, both top loading and front loading. These kilns incidentally were all manufactured here in our kiln workshops. Next one, please. We have an important difference in the way pottery is fired between when we compare industry and studio. If we look at an earthenware body, in industry we will biscuit fire to around 1140 and then select a glaze which is fired at a lower temperature. Now that's done for very good reasons. I can never remember what those reasons are. Oh yes. If you're going to biscuit fire higher than the glaze firing, you're in the glaze firing because you're not reaching the same temperatures. The clay body is not going to warp. It's already gone higher in temperature. It's not going to warp or distort. And so you can pack items together and support them in a way which wouldn't be otherwise possible. Also, if anything is going to warp and distort, it's going to happen during the biscuit firing, and it's cheaper to throw a biscuit pot away than a glazed one. With craft potters use a different technique generally. They biscuit fire to 1000 centigrade and then glaze fire to a higher temperature. They pick a glaze which has a higher temperature firing. And the reason they do that is because if you biscuit fire to 1000 centigrade, the pottery is very porous. You can dip a biscuit pot. You can dip a biscuit pot into glaze, take it out, and that's good suction, and the glaze stays on and firms very quickly. It's more difficult to do that if the biscuit is high fired and fairly vitrified. So, in the studio craft world, they tend to do a low biscuit and a high glaze firing for earthenware, stoneware, and porcelain bodies. The industry does it the other way around. Next slide, please. Temperature control. In industry, we tend to rely upon pyrometric controllers, pyrometers. Measure temperature pretty accurately, measure temperature very accurately. And I think we still use Buller's rings as well, I think, in the industry, I'm sure. Studio potters tend to use autumn cones, little pyramids with a number stamped on the back, which you can relate to a chart, and the number indicates a firing temperature, at which point the cone virtually melts and bends over. And you can see this happening and shut off the kiln at the right time. However, autumn cones, like Buller's rings, they don't measure temperature, they measure heat work. And that really is quite an important distinction, because it mirrors what's happening to your pottery. You can heat a piece of clay up to 1300 centigrade with a blowtorch in a minute or so, but it won't be fired. It takes time for reactions to take place. And the autumn cones measure the heat work that you're putting into the pottery firing. The most accurate way of doing the firings is to pick the appropriate cone for the temperature range you want to fire to, and when it bends, observe the reading on the pyrometer, on the temperature indicator. And then next time you can rely on your temperature indicator and take it to the point that you've already calibrated. Next one, please. Any questions on where we got to so far? Nope. Next one, please. We're going to talk about glazes. Next one. There are many ways of classifying glazes. The most common one is based on whether it contains lead or doesn't contain lead. So we talk of lead-containing glaze or a leadless glaze. We can classify it also by the type of wear to which the glaze is applied. So we talk about raku, terracotta, earthenware, stoneware, porcelain. Or we can classify according to the effect on the finished ware, transparent or clear glaze, opaque, matte, semi-matte or satin vellum. We can classify by firing temperature. We talk about a glaze for 1040 or 1120 or 1260, and that perhaps is the most common classification. But there are others. We can talk about fritted glazes. We'll talk about those in a moment. We can talk about raw glazes. Now here there's a difference in terminology. If you talk to an industrial ceramist, raw glaze means one which doesn't contain any synthetic material. Raw glaze to a studio potter is one that you put onto the clayware and runs fire. But also we can talk of once fire glazes, or we can talk about slip glazes. These are largely the same sort of thing. Once fire glazes invariably contain quite a lot of clay, as do slip glazes. Next slide, please. But let's look at what are glazes. Well, this is a definition. Glazes are thin, generally homogeneous mixtures fused onto the surface of ceramics. In their physical and chemical nature, they're not definite compounds, but complex mixtures which are sometimes described as solid solutions. That covers everything. Next slide, please. To make more sense in a moment. The perfect glaze would be one made of silica, silicon dioxide. But you need a firing temperature of over 1700 centigrade to be able to get it to sort of melt and flow. So in ceramics, what we're concerned with is to find fluxes which we can mix with the silica to achieve a combination which will melt and flow at a much lower temperature range. Silica is plentiful and cheap. It's present in quartz sands and rock veins and combined in clays and most minerals. I think it's the most common material on the Earth's crust, silica, and very hard. It's unusual in that we call it a glass former because when you've melted silica and let it cool down, unlike most other materials which have a definite melting point, copper melts at 1067, not 1068 or 1066, it's at 1067 centigrade under T level. It suddenly changes from a liquid to a solid. Ice suddenly changes from a liquid to a solid at more centigrade, doesn't it? At a precise temperature. Now silica doesn't do that. When silica's cooling down after being molten, it gradually solidifies over quite a wide temperature range. It just becomes more and more solid, just as plastics do. Plastic does the same thing. But it's that property of silica that enables us to use it as a glaze. And we mix it with fluxes to get a temperature range which is usable. This gradual solidification process is why we refer to it as a supercool liquid. But with glazes, we also need a little alumina addition. This helps to stabilise that firing range. But the main addition is the fluxes needed to bring the melting point down to the required temperature range. Now, don't forget, I'm talking a melting point, but it doesn't really melt. Melting really refers to that change at a precise temperature. So, strictly speaking, it doesn't melt. Glazes don't melt, they just gradually become more molten. So glazes are made of silica with fluxes and a little alumina. This one, please. what we were saying on the previous slide. Glazes converted to silica, which is the glass former, combined with fluxes to allow the mix to form a molten glass. We need less flux for high temperature glazes than we would need to use for lower temperature glazes. That's pretty obvious. So we need a flux which can be composed of various compounds of minerals containing sodium, potassium, calcium, barium, zinc, lead, magnesium and boron. And we need some alumina, and we need the glass former, which is silica. Boric oxide, incidentally, is also behaves in the same way as silica, the glass former, as does germanium dioxide. But silica is by far the cheapest and most plentiful glass former. Next slide, please. Now, many naturally occurring materials contain the silica plus the fluxes with the aluminum. Potash feldspar, for example, contains potassium oxide, a very powerful flux, alumina and silica. So Mother Nature has made a glaze for you. And if you fire feldspar up to 1250, 1300 centigrade, it'll be a glassy material. We also had soda feldspar and lime feldspar, often called orthoclase or Wellington amethyte. Strictly speaking, these things don't exist like that. In potash feldspar is mined. You can't look at a mountain and say the molecular formula of that is so-and-so. So these are a bit of an oversimplification. And in fact, potash feldspar is usually called potash feldspar because it has more potash in it than soda. Soda feldspars often contain potash feldspar. But if the principle, we name it according to the one that's present in the biggest amount. And some of these fluxes also are more powerful than other fluxes. You can see that potash feldspar and soda feldspar are capable of getting a good melt with 6 molecules of silica, whereas the lime feldspar can only give the same sort of melt with 2 molecules of silica. It is such a powerful flux. Next slide, please. Nice. The effect of adding fluxes to silica is of interest to geologists and volcanologists as well as ceramists. There are basically 2 sorts of volcanoes in the world. There are the very steep-sided ones like Etna, Vesuvius and Mount Pelée, which have a magma which contains a lot of silica and relatively little flux. And you have the Hawaiian Island type volcanoes, which are much shallower, which contain more flux. In the Hawaiian Island volcano, because the silica is mixed with more flux, you get a more alkaline magma. When the magma reaches the surface, the lava is so fluid that it just runs away down the hillside. Whereas with this one, where you have less flux mixed with the silica, you've got a much thicker, more turgid melt. It quickly solidifies before it can run too far. And so the volcano tends to be characterized by very steep sides. And that's, again, an example of fluxing silica to give a more runny melt. Next slide, please.
Sorry, Harry, can I stop you for a second because we can't hear you now?
Oh, right.
Bear with me.
Okay. Okay, can we pick up on the next slide, please? So, if we want to make stoneware or porcelain glazes, we can use many naturally occurring materials as fluxes. We can use the feldspars, nepheline cyanite, cornice stone, colmanite, whiting, and they can form a glassy glaze with silica. And a typical stoneware glaze, for example, now these are transparent glazes, clear glazes, would be potash feldspar 40%, quartz 30%, whiting 20%, and china clay 10%, what we call the 4321 glaze. It's very popular with studio potters. Now, I mentioned previously potash feldspar is almost a glaze in itself, and I also mentioned that cornice stone is no longer available. It's been substituted by Potclays stone. Next slide, please. So for medium and high temperature glazes, as we've just seen, we're talking about naturally occurring materials which we can use as fluxes to mix with the silica. But for earthenware and low temperature glazes, we need more powerful fluxes, and we need to add more. And the ones that are commonly used, or could be commonly used, I should say, are borax, sodium carbonate, which is sodium ash, and sodium silicate. But there's a problem with those. They're all water soluble. Well, why is that important? Well, when you dip a pot into a glaze, the porous pot sucks in the water, and the glaze particles in suspension in that water are deposited on the surface of the pot. But if you've got something which is dissolved in the water, then they would be taken right with the water stream into the inside of the pot, and when you put the pot down and the pot dries out and the water evaporates away, it brings with it the dissolved salts that have gone into the structure and deposits them on the outside of the glaze. So they effectively unmix themselves. And of course, when pots are drying out, some pots of a pot dry faster than others. A pot with handles, for example, the handle tends to dry out and the rim tends to dry out quicker than the main body. And so you get a preferential evaporation at those points. And so if you've got a dissolved salt in the glaze, then it will be preferentially deposited at those points and won't be an even deposition on the glaze. So what we do is we take the borax, the sodium carbonate or the sodium silicate, mix them with silica and frit them, melt them at a high temperature, heat it up to 1100–1200 centigrade, and the molten material you then pour out into a water bath, and the broken glass fragments, since that's what they are then ground to a powder to produce a frit, what we call a frit. And borax frits are very widely used with earthenware glazes. You could take a borax frit and add 10% of china clay, and you would have a glaze with a firing temperature somewhere between 1020 and 1100 centigrade, depending on the frit. There's another wonderful flux, lead oxide, lead carbonate, and lead. Lead oxide is a wonderful flux, gives bright, glassy, shiny glazes, and it gives a good colour response, and it kills you. It's poisonous. So what we need to do is to make that safe. And to make it safe, We mix it with silica, usually 1 part of lead oxide to 2 parts of silica, to make the lead bisilicate frit in the same way that we do in borax frits. And so there are a range of lead frits on the market, of which the most popular by far, most usable, is lead bisilicate frit. Incidentally, the beautiful colours that you see in Victorian tiles on many buildings, I mean, there's nothing really clever about them. The beautiful colours can still be obtained. It wasn't that they used better colours then, it's just that they used lead glazes then. It's the colour response of the lead glaze which heightens the colours that you get from the pigments applied underneath. And we can match that now with lead frits. One of Potclays glazes in the catalogue, the reference number of it now, 1104. 1104 is it?
2304.
2304 glaze. That simulates very well the sort of glazes that the Victorians used on those tiles, but in a safe form. Incidentally, we talk of lead bisilicate frits and we talk about low solubility glazes. Now, low solubility glazes contain lead, but the lead is present in the form, almost always in the form of lead bisilicate frit. And lead bisilicate frit has to meet the low solubility standard, which demands that less than 5% is dissolved in the stomach juices should you ingest it. And it is really a relatively safe material. People get emotive about lead, of course. But lead bisilicate frit and low solubility glazes, which contain lead bisilicate frit, are really quite safe materials to handle with just elementary rules of personal hygiene. There are also some very alkaline frits which can be made from lithium carbonate or indeed from sodium silicate. Next slide, please. Those are the different lead frits that are available, which I say by far the most popular is PbO2SiO2, the lead bisilicate frit. Next slide, please. This is really just a summary of just what we've been talking about. To make a glaze at lower temperatures, we must use much less silica or use more powerful fluxes. Lead is poisonous, borax is soluble, and so we convert them to frits. And a typical glaze there, which would be a low solubility glaze because it contains lead bisilicate, contains 25% of lead bisilicate frit. We've also put in 65% of borax frit and 10% of china clay. The china clay introduces alumina and silica, but it's of great practical importance. It helps stop the glaze from settling out. It's clay, and so it helps you keep everything in suspension. Next slide, please. So we've got a transparent glazes. How do we make them white or opaque? Well, we had an opacifier, of which tin oxide is the best. If you add 10% of tin oxide to a glaze, two things will happen. Firstly, it'll make it a hell of a lot more expensive. But secondly, it will fire white. Very predictable. The Delft white ware that you see on the Antiques Roadshow is a tin opacified lead glaze. We can use zircon. It's slightly cheaper, but you need about 1.5 times as much to achieve the same level of opacification. So it's a bit marginal price-wise. Incidentally, some textbooks refer to using zirconium oxide, which I can't understand because zircon, which is zirconium silicate, is cheaper, and if you add zircon oxide, zirconium oxide, it converts to zirconium silicate as you combine with the silicon in the glaze anyway. So we use tin oxide or zircon as opacifiers. Titanium oxide and rutil are also good opacifiers, but they impart a little colour. Titanium oxide makes an ivory sort of colour. Rutil gives you browns. Now the opacification depends upon the cooling rate with zircon and rutil and titanium, but not with tin oxide. So you put 10% tin oxide in and it will give you a good white. With the other opacifiers, they crystallise out of solution as the glaze is cooling after firing, so that if the glaze was cooled too quickly, then you only get partial opacification. You need the glaze to cool down reasonably slowly for the crystals to grow and produce the full effect of the opacifier. But that doesn't happen with tin. And we can add colouring pigments to glazes, with glaze stains or what we call oxides, which are oxides of copper, iron, cobalt, manganese. And there's a wide range of prepared glaze stains, which I think we have on the next slide, please. It must be a later slide. It's okay, we'll stick where we are. Glaze manufacture and preparation. Now, glazes are typically manufactured using either ball mills or dry blending. Whilst traditionally sold in a powder form, a large proportion of the studio craft market is now beginning to use the glaze in a prepared form, a wet glaze. But if powder glaze is supplied, which is the cheapest way of buying glaze, how do we convert it to a glaze ready for dipping? Well, what the studio potter does is he adds the powder to water, plenty of water in a bucket or a bin. People always say, what's the ratio of water to powder to add? Well, it doesn't apply. What we do, we add the powder into plenty of water and then stick it on and give it a good stir. So we mix it and then we pour it through a sieve into another bin. The reason we add plenty of water is so that it pours through the sieve more easily. So we've now got a bin full of sieved glaze. And we leave that to settle overnight. And the following morning we can decant off the water from the top and give what remains a stir, and now it'll probably be too thick. And then we add a little bit of water back until we get it to the required dipping consistency, which we can determine by just doing a sample dip. Now, where necessary, we can add calcium chloride or magnesium sulfate as flocculants. With the lower temperature glazes particularly, where you have frits, these tend to settle out of suspension very quickly. And they settle out, they can go quite hard. So hard that when you put your hand in it, it's almost like lifting up tiles of solid glaze at the bottom. And you can avoid that by adding a saturated solution of calcium chloride. You get 2-3 dessert spoonfuls of calcium chloride into a mug of water. Just leave it to stand, by which time there will be some undissolved material at the bottom, which tells you that the liquid is now saturated. And that it's liquid that we use. And you add 4-8 teaspoonfuls per gallon of glaze, and it's stops the glaze from, it flocculates the glaze particles, so that when they drop to the bottom, that they don't pack together very closely. They pack in a much more loose arrangement, and you put your hand down and knock them up. And magnesium sulfate, which is Epsom salts. Now we all know that Epsom salts loosens things, and it does with glazes. You put some Epsom salt in just the same way, and it'll give you a looser arrangement. In practice, because it's a flocculant, it causes the glaze to settle actually at a slightly faster rate. And so sometimes we have a little bentonite too, which is a very fine suspension of clay particles, which slows down the settling rate. But the important thing is adding those stops the glaze from setting hard at the bottom of the containers. In industry, of course, we use recirculation pumps. We're pumping the glaze around continually and through sips. So it's a problem which never really develops in the industry. Now occasionally we might need to add SCMC, sodium carboxymethylcellulose, as a glaze binder. When I worked at Twyford's, the ware coming down to the kilns is come down on a conveyor belt, and a kiln loader, kiln placer, would pick up a large closet, white glazed large closet, and put it on the kiln cover. The next tray coming down might have a blue one. Pick that one up and put that one on. The next one might be a yellow one. You pick that. Nowadays you need a white, don't they? But in those days a lot of colour glazes. Now of course the problem is you transfer glaze on your fingers from one pot to another. And so what we used to do was to mix in about 2.5% of sodium carboxymethylcellulose. It's a glaze binder. Very similar to polysol wallpaper paste, which makes a good alternative. And this makes the glaze go like eggshell, so that you don't get that dusty glaze surface and you don't get the colour transfer. But if you continue with the dosage, if you add up to about 5% of glaze binder, then the glaze goes like gloss paint compared to milk. It goes very creamy, and you can make the glaze suitable for brushing. SCMC has the effect of causing the glaze to hold on to its water. So when you paint with glaze with SCMC in it, it doesn't dry out so quickly, and the brush marks, because the glaze stays wet longer, just flow out. So it's used as a basis of brush-on glazes. Incidentally, one time we used to use gum arabic and gum tragacanth, but of course they decompose in a warm room, and they leave a smell which has to be experienced to be believed. SCMC in theory shouldn't decompose. Don't you believe it? We used to have the glaze delivered to the what we call the colour shops, where colour glazes were sprayed onto ware, and they came in a rubber tub that was diameter inside a metal frame, and a rubber lid with a metal frame on the top and over centre clips to hold the whole thing airtight. And the tub would come in, we'd take the lid off, and we'd take it to the mixers where we added the SCMC, and stir it in with powered mixers, and then it would go onto the sprayers. On this day, one must have been perhaps at the end of the day. The sprayer didn't need it, but it was somehow put back behind the stockpile. And there it stood for a month or two, and when the chap came to move it out, he pulled this drum out and he noticed that it was bulging at the seams, it was bulging through the metal frame. On the lid, it was bulging through the lid. And at this point, he took leave of his senses. He unclipped the lid. Well, of course, the explosion was actually swamped him. The girls working 15 feet away, they down tools and walked out because of the smell. And so SCMC does decompose. They say it doesn't, but it does. Okay. Yeah, these are showing just some of the different colours that are available, glaze and body stains. You can now get bright reds, which were not possible at one time, using encapsulated colours. So a good range of colours, about 5% of any of those colours added into glaze will give you a colour glaze. Next slide please. And a wide range of earthenware glazes. Next one please. Stoneware glazes. More muted colours we tend to get from stoneware.
Hold the phone, Barry, please.
Thank you. Yeah, more muted colours you tend to get from stoneware glazes. Next one please. And this is a range of brush-on glazes. Quite a wide range of colour. Most of these are designed really for use on earthenware clay bodies. And certainly it's true that at earthenware you can get a far wider range of glazes and glaze colours than you can get at higher temperatures. At the end?
No? Yes.
Questions?
We'll take questions after.